Thank you. Oh, hello, everyone. Thank you for coming. The outline of this presentation is as follows. First, I'm going to present an introduction. Then I'm going to introduce the approach of object recognition using template matching methods. Then we're going to present the proposed approach. Next, the obtained results, and finally, the conclusions. Mobile robots can be considered as an automatic machines that can move through a given environment. Commonly, these robots contain several sensors to capture information from the environment in order to make decisions. In this context, the use of vision sensor is essential for to represent and describe the environment and to perform safe navigation. A mobile robot with vision sensors, first the imaging device captures image of the environment to detect and describe salient features. Then this information is employed to perform several essential tasks, for instance, construction of maps, the localization of the robot within the map, object recognition and localization, target tracking, path planning and navigation, and the control of the robot actuators. So in this work, we identify the task of object recognition and tracking as essential for robot navigation. So in the case of object recognition, we can see, for instance, a set of different views of an object of interest to be detected and tracked. So in this case, object recognition can be defined as an action to solve three essential tasks. So we capture an observed scene, and the first task is to detect the presence of the object in the scene. Then the task of localization consists in estimate the exact coordinates of the target in the scene. And finally, classifications, which assigns the detected object to a proper category. Target tracking or object tracking consists in estimate state trajectory of the target while it moves through a detection zone. So the main challenges in robot navigation based on object recognition and tracking consist in the presence of additive noise and background clutter in the scene, geometric modifications of the target, presence of change in illumination, temporal or partial occlusions of the target, and real-time requirements. So a tracking algorithm for robust vision must be robust, accurate, and fast. So a common approach to perform or to construct object recognition and tracking algorithms for robot vision is by using the detection and descriptions of interest points of the scene. A common or well-known method for this is the scale invariant feature transform, or SIFT, or the speed up robust feature, SORF. Well-known tracking algorithms that are very successful is, for instance, the tracking learning detection, or TLD, or the tracking method using online multiple instant learning. So we are proposing an alternative approach based on template matching to construct an algorithm that for a reliable object recognition and tracking applied to robot navigation. So in this case, we are going to present a new algorithm for object tracking based on template matching. In this case, the proposed filtering is adapted dynamically to each capture frame of the scene using information of current and past state estimation of the target. And this algorithm will going to be implemented on a mobile robot for autonomous navigation. In this case, is by following a reference object. So the block diagram of an object recognition system based on template matching is as follows. First, an input images. An input image is transformed to the frequency domain by means of the Fourier transform. The resultant spectrum is multiplied by a match filter, and the filter spectrum is transformed to the space domain using the inverse Fourier transform. This part of the system is the processor or the correlator, and then the output correlation function of this processor is analyzed in order to take decisions. In this case, we search for the coordinates of the maximum intensity value of the output function, and these are estimates of the coordinates of the target in the scene. And if the maximum correlation intensity value overpasses a threshold, then we consider that the target is detected. Otherwise, it's rejected. So this part of the system is the decision making. This approach has some advantage. For instance, can be implemented efficiently using an hybrid optodigital processor, for instance, the 4F correlator, or also can be implemented by exploring massive parallelism in dedicated digital architectures such as GPUs or FPGAs. So in this case, the input scene, a capture input scene, can be modeled according to the non-overlapping signal model as follows. In this case, a target is located at unknown coordinates and embedded on a disjoint background, and the whole scene is corrupted by additive noise. So in this work, first we encode a color capture scene into a single channel complex function. So in this case, we're going to present the input image coded in one single channel instead of processing 3 independent color channels. In order to construct the match filter, we use the composed filter approach. In this case, we have several available views of the target to be recognized, and the filter is constructed using a supervised training process. So different views of the target, expected distortion of the target can be recognized with a single filter. So the complexity of the overall recognition system can be reduced. So assume that this is a set of different available views of the target to be recognized, expressed in the frequency domain. Moreover, we have a set of desired output correlation planes expressed in the frequency domain, which the designed filter needs to be produced in response of the training images. So the minimum output sum of square error or Mohs filter is obtained by solving this functional. So the resultant filter is this one. So the block diagram of the proposed algorithm is as follows. First, the first stage is initialization, which consists in capture scene frame or scene images. select the target, and perform the color codifications. Then the tracking starts by firstly constructing the filter, in this case the MOSE filter, capture a new frame of the scene, perform color codification, perform the correlation operation to detect and locate the coordinates of the target. Then we predict the coordinates of the target for the next frame and adapt the filter, and this process is iteratively repeated for each coming frame. So next, I'm going to show you the operation of the algorithm. So first, we select the target, and then the tracking starts. So this is the input scene. Of course, in this case, we are not performing the color codification. This is the adaptive template match filter, and this is the output correlation function. So as we mentioned, the maximum correlation value indicates the coordinates of the target in the scene. In this case, is in this region of interest. So this algorithm is able to manage partial occlusions of the target, like in this case. So we evaluate the performance of this algorithm in several synthetic color image sequences, like these ones. So we test different well-known filters. For instance, the minimum average correlation energy filter, the optimal trade-off synthetic discriminant function filter, and the MOSE filter that I explained before. So we evaluate the performance of these filters in the proposed algorithm in these sequences, and we evaluate the discrimination capability of the filter and also the location error. So in this case, when in a single frame, the obtained location error is less than 5 and the discrimination capability is greater than 0.5, the target is considered as detected. So in this case, the MOSE filter yields the best results. Now, in order to test this algorithm in experimental platform, we construct a little mobile robot using the AmigoBot platform. We employ a NVIDIA Jetson TK1 processing platform. We use Python with OpenCV and area programming languages. We use as an imaging device a conventional Logitech camera, and we construct several mounting and mechanical pieces on a 3D printer. And you can see the test platform. So this is an initial or preliminary test. So this is the robot view, and this is the reference object. When the operation of the robot starts, it detects the target and approaches to them to a pre-specified distance. When the reference object moves, then the robots try to reach them to the predefined distance. This is another test in laboratory test. So in this case, the robot needs to track or follow this person. So in in this moment, the robot loses the target, and they find it again and reestablish it. So the person moves around this room, and the robot is following. Okay, conclusions. So we present an algorithm for object recognition and tracking based on template match filtering. This algorithm is dynamically adapted to each capture frame, and no previous training process is required. We test several composed match filters, and the most filter is identified as a feasible option. The performance of the proposed algorithm was tested in synthetic image sequence in terms of objective measures. And the usefulness of the proposed algorithm was verified experimentally on a mobile robot for autonomous navigation. So that's all. Thank you very much.